Hi, in this video, I'm going to show you how to leverage the calculation methodology that goes into a power spectral density to scale it to kind of look like a FFT, a Fourier transform, that have the output units that match the input units. And this gives you some benefits to power spectral density while also getting some of the benefits of kind of results that you'd expect from a typical FFT. So this is part of a four-part series on power spectral densities, frequency analysis, etc. So please subscribe and check out the other videos as well. I'm going to use NDAC's open source library here. So it's free, it's open source. Please install it. Pip install NDAC. I'm installing the development branch because it's a little bit more advanced than the release version, and you can do the same, or you can wait for the release version too. So first thing I'm going to do is I'm going to generate a couple signals. One is noise content from 10 to 50 hertz. The other is two sine dwells, one at 30 hertz and one at 80.25 hertz. And then the last is adding the sine tones on top of the random. And a big takeaway here I want people to have is that in the time domain, you can't really see any of this 10 hertz, 50 hertz sine tones information. This is the first thing people typically do when they have data, vibration data, is plot in the time domain, and I encourage people to do that. It is the first thing. You can identify time ranges you maybe want to look at, but in order to see the frequency content, you need to actually do that next step. So how do we do that? We're going to be using this function called aggregate FFT, and we call it aggregate FFT because it's basically averaging or aggregating many different FFTs for a given segment. This function, you pass in the time domain data. So it's acceleration, a couple different columns in a data frame, and then it was the time index, and then you specify the bin width, and then you get returned this Fourier transform results with bin widths that you defined of 1 hertz spaced, and then the results. So, and then if I plot it, we see here, we'll look at this sine tone. This is kind of what we'd expect. I added a 30 hertz 1G sine wave, and I see that perfectly, 30 hertz 1G, that's great. Now, this part's a little interesting though, is my 80.25 hertz sine wave, my peak value is showing as 0.9 Gs. And that's because my frequency bin didn't perfectly align with the frequency at which the sine tone happened at. And you can kind of see that it basically leaked into other bins. And we see that here, this kind of, at the 30 hertz one, it's very triangular. Here, there's a bit of a curve on both sides, meaning that peak sine dwell or tone is not exactly at the point at which the frequency was plotted at and calculated for. So, but I can kind of see that already, and it's still pretty close to my 1G that I'm expecting. Now here's the noise data. See this nice 10 hertz to 50 hertz like we'd expect, and then the sine on random. Okay, so I'm going to do the same. I'm going to calculate that for a bunch of different time ranges and different bin widths, because that's what I can specify with this function, aggregate FFT. And if I look at this middle column, the big takeaway here is as I change, it looks like I've only really plotted one line, but if I start here, this is when I do 2 seconds, this is 3 seconds, or 8 seconds, 9 seconds, 10 seconds. They're all the same result, and that's really powerful and encouraging that this methodology allows us to compare different time ranges a lot better. As I change my frequency bin width from 0.5 hertz to 2 hertz, you notice that the values stay pretty constant. The only change is that my 2 hertz one, I start to be spanning more completely that peak frequency of 80.25 hertz. So I now am at 0.97 Gs as opposed to when I'm at a bin width of 0.5 that I kind of have to span across a little bit more. And so it's a wider and shorter peak for that particular thing. So That's a big takeaway though. For this methodology is great for the sine tones, the peak frequencies, and it gives you values of what you'd expect. I put in 1G at 30 hertz and 80.25, and I'm now seeing that pretty close in the frequency domain. It might be a little lower because my frequency bin didn't exactly align with the that frequency, but it's still pretty close, and it does a good job. So this is really nice. The one problem though is you'll notice as I change my bin width here, the values of the random content are changing. And that's because this isn't a density, so we would need to be careful at comparing the output of this to another data set if we didn't use the same bin width. And so that's why this methodology is not necessarily recommended for looking at random content. It can be okay though if you make sure that you compare it to random content using the same bin width. All right, so how is this calculated? What makes this so special? Well, it's the same methodology of doing a power spectral density where there's all these segments, overlapping segments, and then you apply a window, but I'll show you that for this method, we actually don't want to apply a Hanning window because it will give us funny amplitudes, which we can kind of get around with scaling. But then we square and normalize the results, and then basically go from a density to just by getting rid of the density element by multiplying by the frequency bin width and then taking the square root. So here's my first step. I'm adding in all these segments. It looks different than before if you looked at the power spectral density video because there's no windowing really applied. I'm just taking the full time range. I'm still doing overlapping segments. You see here, goes from 1.5 to 2. So I get more time ranges to then average and get a cleaner result. That's the first step. The second step is then computing these Fourier transforms for each one of those segments. And then we average them together after squaring them, doing some scaling there as necessary, and we get this output. And we see here for each different time range, you get these that can be really messy results. But as we average them all, we get that output of what we were hoping for, about 1G output at 30 hertz and 80.25. Now there's another function here you can use to calculate a rolling FFT or a spectrogram, and so that's in our library, and I'll show that more in another video in this series. But I wanted to include it here as a way to kind of skip a couple steps if you wanted to. Here's showing an animation of the different frequency ranges. Not all that helpful when the frequency content isn't really changing over time, but it's still a nice way to look at it. All right, now let's look at some real world data. This is from a surgical instrument, so I'm loading in that content, and then I applied a high pass filter to get rid of any DC bias, and I plotted it. You see here it's pretty steady over this time range. So then I plotted just a tenth of a second. Would I do a tenth of a second? Yeah, a tenth of a second. You notice that there's these 7 peaks in that tenth of a second. So I should be expecting when I do an FFT to see some resonance at 70 or so hertz. But other than that, I can't tell too much else about the frequency content in here. There's a lot going on, but admittedly, you can't tell that there's a pretty predominant peak around 70 hertz. So again, I'm going to pass this time domain data into this function, fft.aggregateFFT. I'll specify a bin width of 1. You can do a lower bin width, or, a finer one, 0.5, 0.25 if you like, go wider, but I like to use 1. And then I'm plotting it, and you see here this nice 73 hertz peak, and we can tell it's pretty spot on, although it's not perfect because I don't have a completely triangular result here, but we know that there's about a 1G, 1.15G, 73 hertz sine tone that's predominant, and then there's some harmonics of that, and that's kind of what's making the signal not look as clean as possible, but pretty good. And that is how to calculate this aggregate FFT. It's leveraging the methodology that goes into a power spectral density to scale it in such a way that gets the results of that have output units that match your input units. So it looks like that, kind of Fourier transform, and you get nice peaks at the amplitudes you'd expect. Again, please subscribe to our videos here in our channel, because we're going to do some other videos comparing the FFT, the power spectral density, this hybrid method for different time ranges and different recording files. And we're also going to analyze some data that has changing frequency content over time. Thanks.